Good morning, students. This is our second lecture on chapter 13, that is magnetic effects of electric current. Okay. In the previous class, in the first class, we have studied about the magnetic field lines. Okay. How's the field lines forms, the imaginary field lines. Okay. And with the help of bar magnet, we have seen the field line patterns. Okay, around a bar magnet. Magnetic field due to a current carry conductor. Okay, we have seen the concentric circles are formed if we are taking any conductor and it has some current, then concentric circles shows the magnetic field. Okay, in this diagram this concentric circle shows the magnetic field. Okay, the patterns of concentric circles indicate the field lines. Okay, the farther we move the compass, the more the size of the circles. Okay, now we are going to study about the right hand thumb rule. So who gave this rule? Gave this rule. Maxwell was a scientist who gave this right hand thumb rule to determine the direction. Okay, how the magnetic fields are formed due to the flow of current. So how we take its conventions. Okay, in this diagram you can see here thumb is pointing towards the current. Okay, and it's the direction of the fingers shows the direction of the magnetic field. Okay, the wrapping of the fingers shows the magnetic field. Okay, that imagine that you are holding a current carrying straight conductor in your right hand such that the thumb point towards the direction of current. Thumb is pointing towards the direction of current. Then when we wrap our fingers around the conductor in the direction of the field lines of the magnetic field. Okay, therefore this is the right hand thumb rule. Okay, so our thumb of the right hand indicates the direction of current and wrapping of our finger indicates the magnetic field. Okay, we have to point the thumb towards the direction of current. Okay, if a straight carrying conductor uh, current carrying conductor is held in the right hand in such a way that a thumb points along the conductor in the direction of the current, then the direction of the curled fingers or wrapping of the fingers of the hand gives the direction of the magnetic lines of field lines of the magnetic field. This is the Maxwell's right hand thumb rule. Okay, so here uh, the direction we can find through this rule, right hand thumb rule. Okay, east, west or north, south directions. Okay, now the magnetic field patterns. The patterns of magnetic field here shown in the 13.8. The magnetic field lines of the field produced by current carrying circular loop. Here the circular loop is placed here. Okay, so here the what is the formation? The strength of the magnetic field is inversely proportional to the डिस्टेंस फ्रॉम इट. ओके, सो डिस्टेंस जितनी ज़्यादा होगी स्ट्रेंथ उतनी ही कम होती जाएगी. ठीक है, so strength of the magnetic field produced by the current carrying circular loop is inversely proportional to the distance. Second factor on which this magnetic field depends is the at a point is directly proportional to the current passing through it. Okay, the magnetic field is proportional to the current and inversely proportional to the distance. And the magnetic field strength can be increased in the circular loops by increasing the number of turns of wire in the coil. Okay, if we increase the number of turns of wire, we can increase the magnetic field strength. Okay, if n number of identical circular wires are used, then field produced is much higher. Okay, and a circular coil carrying current behaves like a thin disc. Okay, it behaves like a thin disc and a shaped magnet, and one face of this disc shows the north pole and another face is the south pole. Okay, this is shown by the circular loop, the patterns of the electric field lines. Okay, at the edges there is a circular concentric circles, and near the north and south axis the directions are field lines are is shown. Okay, so big circles would be appear as a straight lines. The big circles are appearing as a straight lines here in this pattern. This rule is also called the Maxwell's corkscrew rule. If we consider ourselves driving corkscrew in the direction of the current, then the direction of the corkscrew is the direction of the magnetic field. Okay, so we know that the magnetic field produced by current carrying wire at a given point depends directly on the current passing through it. Okay, whenever we pass the current through it, then it produces a magnetic field, and if there is a circular coil having n turns, the field produces n times as large. So the magnetic field depends on the number of turns of this circular coil, because the current in each circular turn has the same direction. Okay, current in each circular turn has the same direction, and the field due to each turn then just adds up. The field will get adds up when we increase the number of turns of the coil. On this property of increasing the number of turns of the coil, we made a we study about the solenoid. Okay, solenoid is the device which is made up of this number of turns of the coil. Coil of many circular turns of insulated copper wire wrapped closely in the shape of cylinder is called a solenoid. What is a solenoid? A coil of many turns, okay, many circular turns. Why these circular turns are made? Circular turns are made to increase the strength of the magnetic field. So what we are making here, we are making here a solenoid which is a cylindrical coil of many circular turns. Okay, cylindrical coil of many circular turns of insulated copper wire. And you can see the patterns of magnetic fields around this current carrying solenoid is in the figure 13.10. Okay, now you can compare the field with the magnetic field around a bar magnet. Okay, they are similar. One end of the solenoid behaves as the magnetic north pole, and the other behaves as the south pole. Okay, like the bar magnet, the solenoid also have one north and one south pole. The field lines inside the solenoid are in the form of parallel straight lines. The field lines which are inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is same at all points inside the solenoid. Okay, this indicates that the magnetic field is same at all the points inside the solenoid. Field is uniform inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron. Okay, so by the use of this solenoid, or using the strong magnetic field by the solenoid, we can magnetize a piece of magnetic material of soft iron. Okay, when this soft iron is placed inside this coil, that is solenoid coil, we can make it a electromagnet. Okay, the magnet so formed is called as the electromagnet. A current carrying solenoid coil is used to magnetize steel rod inside it, and it is an electromagnet. Okay, so solenoid, with the help of solenoid, we can make an electromagnet. Now force on a current carrying conductor in a magnetic field. Okay, so force on a current carrying conductor uh, in an magnetic field, we have to see here that the electric current is nothing but flow of electrons. That means the moving electrons through a conductor produces a magnetic field. If this current carrying conductor is now placed in a magnetic field, then it will experience a force which can either be attractive or repulsive. Okay, whenever this current carrying conductor is placed in a magnetic field, it will either experience a force. Okay, a force is experienced by this or current carrying conductor. It can be either attractive or repulsive. Okay, so you can see here the magnetic field given by the horseshoe magnet, that is north south, and when we are placing this current carrying conductor on hanging in this current carrying rod, okay, AB, experiences force perpendicular to its length in the magnetic field. So this is principle we are using in the next topics. Okay, force is experienced. We have to conclude from this that the force is experienced by the current carrying conductor when it is placed in the magnetic field. Okay, the displacement of the rod in the above entity suggests that a force is exerted. Okay, force is exerted on the current carrying aluminum rod when it is placed in a magnetic field. It also suggests that direction of force is also reversed when the direction of current through the conductor is reversed. Okay, here in this activity, if we move the magnet, the direction of the current is reversed and it will tilt on the other side. So changing the direction of the magnetic field to vertically downwards by interchanging the two poles of magnet, one can observe that direction of force acting on the current carrying rod gets reversed. Okay, it shows the direction of force on the conductor depends on the direction of current and the direction of magnetic field. So here comes the Fleming's left hand rule about this force on the current carrying conductor which when placed in the magnetic field. Okay, so Fleming's left hand rule says that according to this rule, stretch the thumb, forefinger and middle finger, okay, of your left hand. Okay, stretch the forefinger, middle finger and thumb of your left hand. If the first finger points in the direction of magnetic field, okay, and the second finger in the direction of current, then the thumb will point towards in the direction in the direction of the motion or the force acting on the conductor. What is the amount of force acting on the conductor or what is the direction of the force on this conductor, we can conclude by this, calculate by this uh, Fleming's left hand rule. Okay, if we know the direction of the magnetic field, we will take it on the first finger and then with the middle finger we point out the current direction and then the thumb will give us the direction of the motion or the force on this current carrying conductor. So it is an important rule, Fleming's left hand rule. Okay, and these devices that use current carrying conductors and magnetic fields includes electric motor, electric generator, loudspeakers, microphones and measuring instruments. All these instruments works on this principle. Okay, so this force is very important, which is on a current carrying conductor in a magnetic field. Okay, so the strength, force, factors affecting the force. What are the factors affecting this force? The force is directly proportional to the current. Okay, how the amount of current increases, the force will be increases. Okay, length of the conductor, if we have taken the greater the length of the conductor, greater will be the force, and if the stronger the magnetic field, the greater will be the force. The force depends on the electric current and electric current length and magnetic field strength. Okay, so this is the Fleming's left hand rule. Okay, electric current always produces a magnetic field. Even weak ion currents that travels around the nerve cells in our body produces magnetic field. Okay, electric current always produces a magnetic field. Okay, so it is a topic, magnetism in medicine. When we touch something, our nerves carry an electric impulse to the muscles we need to use. This impulse produces a temporary magnetic field. These fields are very weak and are about 1/1000th of the Earth's magnetic field. Two main organs in the human body where the magnetic field produces significant are the heart and the brain. The magnetic field inside the body forms the basis of obtaining the images of different body parts. Okay, and this is done is using technique called magnetic resonance imaging, MRI. Analysis of these images helps in medical diagnosis. Magnetism has thus got important use in medicine. Okay, so this is the importance of this force which is developed by placing a current carrying conductor in the magnetic field. Okay, so force will be developed and we can determine the direction of force by the Fleming's left hand rule. Okay, today we have studied about the solenoid, electromagnets and the Fleming left hand rules. Okay, and the current carrying circular loops. The solenoid is nothing but a form of cylindrically shaped uh, circular coils where many number of circular coils are added of conductor like copper. Okay, so this phenomenon of producing of electric field and magnetic field produces the force is used in our next topic, that is the electric motor, which we will discuss in our next class. Okay, thank you, have a nice day.